The thing that's going to break your reality today isn't some mystical mumbo-jumbo. It's what nature actually does, and it's far more interesting than anything anyone could make up. So let me start with a simple question. When light goes from point A to point B, how does it go? You say, well, it goes in a straight line, obviously. And I say, why a straight line? And you say, because that's the shortest path. And I say, aha, now we're getting somewhere. But who told the light to take the shortest path? See, this is where it gets interesting. Back in the 1600s, a fellow named Feynman said, light takes the path of least time. Not shortest distance, but least time. And this works beautifully for explaining how light bends when it goes into water, how mirrors work, all of that. But it's still the same idea. Light somehow knows to take one particular path. But here's the thing that'll blow your mind. Light doesn't take one path. It doesn't move through space the way you think it does at all. Let me explain what I mean. Suppose I want to figure out the probability that a photon, that's a particle of light, gets from point A to point B. You might think, well, I'll just calculate which path it takes and then I'll know. But that's not how nature works. What nature actually does is this. The photon explores every possible path, not just the straight one, not just the curved ones, every single path, the one that goes straight, the one that curves a little to the left, the one that goes way out to Jupiter and comes back, the one that does loop-de-loops, all of them. Now you're thinking, Feynman's lost his marbles. But wait, I haven't told you the beautiful part yet. Each path contributes something I call an amplitude. Think of it like a little arrow that spins around like the hand of a clock. For each path the photon could take, we draw one of these arrows. The arrow has a certain length, which stays the same for all paths in empty space. But the direction it points changes, depending on how much time that path takes. Here's the crucial bit. The arrow rotates as the photon travels along that path. How fast? At a rate determined by the frequency of the light. For yellow light, if you travel an extra 570 nanometers, that's about 500 times smaller than the width of a human hair. The arrow makes one complete rotation and comes back to where it started. Now here's where it gets really beautiful. When you have a path that's close to the straight line, the classical path, and you compare it to a nearby path that's just slightly different, those two paths take almost the same amount of time. Almost the same. So their little arrows point in almost the same direction. You add them together and they add up. But look what happens when you take a path way over here that curves way out to the side and you compare it to another crazy path right next to it. Well, one takes a bit longer, one takes a bit less time, and their arrows point in completely different directions. When you add arrows pointing in different directions, they cancel out. They interfere destructively, as we say. So you add up all these arrows, and I mean all of them from every conceivable path, and what do you get? Almost all of them cancel out. The only ones that survive are the paths close to the classical path, where neighboring paths take nearly the same time, and their arrows all point roughly the same direction. This is why you see light going in straight lines, not because it takes the straight path, but because all the other paths cancel each other out in this marvelous conspiracy of interference. You can actually check this. Take a mirror. Now you think the light bounces off the center of the mirror because that's the shortest path, right? Wrong. Here's an experiment you can do. Take that mirror and roughen up the center part. Make it so the light can't reflect from there. What happens? The light still gets to your eye. How? Because the parts of the mirror near the edge can still do it. Their paths take almost the same time as the center, so their arrows all point in similar directions and add up. But if you roughen up parts of the mirror that have paths taking very different times, nothing much happens, because those parts were canceling out anyway. This is not some mathematical trick, by the way. This is what nature does. Every single photon that hits your eye right now from that lamp did this. It explored every possible way to get to your eye, and only the paths that constructively interfere actually contributed to the probability you'd see it. Now let me tell you why this really breaks your reality. You see, in your everyday experience, things go from A to B along a path. A ball flies through the air on a nice parabolic arc. A car drives down the road. But at the quantum level, the level of photons and electrons, there's no such thing as the path. There's only a sum over all possible paths. The photon doesn't move through space from A to B. That's human language trying to describe something that doesn't work that way. The photon starts at A, and then it ends up at B, and all we can calculate is the probability of that happening by adding up the amplitudes for every possible way it could have happened. When I say every possible way, I mean it. Paths where the photon goes backwards in time, paths where it bounces around the room 17 times, paths where it travels faster than light, slower than light, or not at all. Every single one contributes an amplitude. Now, most of these crazy paths cancel out with other crazy paths nearby, which is why we don't notice them. But they're there in the mathematics, and they're necessary to get the right answer. This is not just for photons, by the way. Electrons do it. Atoms do it. Everything does it. It's just that for big things like you and me, the number of atoms is so huge, and they're all doing this crazy sum over paths that everything cancels out except a tiny, tiny range of classical paths. That's why you don't quantum mechanically tunnel through your chair when you sit down. Well, technically you do, but the probability is so fantastically small that you'd have to wait longer than the age of the universe to see it happen. But for a single photon or a single electron, you can see these effects. Send an electron through two slits, and it interferes with itself because it went through both slits. Or more accurately, the amplitude for going through the left slit interferes with the amplitude for going through the right slit. Now, you might ask Professor Feynman, can we watch which path the photon actually takes? And that's a very good question. The answer is, as soon as you try to watch, as soon as you put a detector that says, aha, the photon went this way, the whole interference pattern disappears. Why? Because by measuring which path it took, you've destroyed the ability of the different paths to interfere with each other. It's like this. Imagine you're adding up all these little arrows. As long as you're adding amplitudes, these complex numbers with magnitude and direction, you can get interference. But the moment you make a measurement, you're asking nature to commit, did it go this way or that way? And nature gives you a probability, the square of the amplitude. Once you square it, you lose the phase information, you lose the direction of the arrow, and you lose the ability to interfere. This is what we mean when we say quantum mechanics is weird. It's not that photons are sometimes particles and sometimes waves. That's not quite right. The photon is always described by these amplitudes that behave mathematically like waves. They can interfere. But when you measure, you get a definite result. It's here or it's there, like a particle. The thing is, between measurements, you can't say the photon is anywhere. It's not hiding somewhere in space, following some definite path we just don't know. The mathematics doesn't work that way. The amplitudes for all the different possibilities are all equally real, and they all contribute to what happens next. Here's something that really drives this home. The amplitude for a photon to go from point A to point B depends on the time between when it leaves A and when it arrives at B, not the distance, the time. And the phase of this amplitude, the direction the little arrow points, rotates at a rate determined by the photon's energy. High-energy photons, like X-rays, have arrows that rotate very fast. Low-energy photons, like radio waves, have arrows that rotate slowly. This connection between energy and the rate of rotation of the amplitude, this is the frequency of the light. When we say light has a frequency, we're talking about this rotation rate. And the wavelength, that's how far the photon has to travel for the arrow to make one complete rotation. So when you see light behaving like a wave, what you're seeing is the result of this interference of all these amplitudes. The wave isn't out there in space. The wave is in the probability amplitude. It's in the mathematics of how likely different things are to happen. I want to make something clear, though. This isn't philosophy. This isn't interpretation. This is what you have to calculate to get the right answer. You can check it experimentally. Every prediction quantum electrodynamics makes, and it makes predictions to 11 decimal places, comes from this process of summing over all possible paths. The reason I say this breaks your reality is because everything you thought you understood about how things move from place to place is wrong at the fundamental level. At the bottom of everything, particles don't travel along paths. They don't move through space. They start somewhere, they end somewhere else. And to calculate the probability of that happening, you have to include every possible intermediate history, no matter how crazy it seems. And yet, paradoxically, this gives you back classical physics. When you have lots of particles, or when the action, that's a technical term for the classical path, is very large compared to Planck's constant, all those quantum amplitudes add up in such a way that you get back Newton's laws. You get back straight lines. You get back everything behaving sensibly. It's like nature plays this incredible joke on us. At the small scale, everything is probabilistic. Everything is this sum over all possibilities. Everything interferes with everything else. But at our scale, all that washes out, and we get billiard balls that move in straight lines and clocks that tick regularly. The final thing I want to tell you is this. We don't know why nature works this way. We know that it does. The experiments are absolutely clear. We know how to calculate with it. I got a Nobel Prize for figuring out how to do these calculations efficiently for photons and electrons. But why? Why does nature sum over all paths? Why do amplitudes interfere? We don't know. What I can tell you is that this is the simplest way we've found to describe what happens. And it's not just simple, it's beautiful. The idea that a photon explores every possible path, that all these paths contribute, that the classical path emerges from the conspiracy of quantum interference. That's beautiful. That tells you something about how nature is put together at the deepest level. So the next time you turn on a light, remember, those photons hitting your eye didn't simply travel straight from the bulb to your retina. In a sense, each one of them tried every possible route, bouncing off the walls, going around the room, even crazy paths you can't imagine. And only because most of these crazy paths canceled each other out. Did you end up seeing what looks like a beam of light traveling in a straight line? Light doesn't move through space the way you think it does. Space and time and paths, these are all just scaffolding we use to do the calculation. The real story is about amplitudes, phases, and interference. That's what nature is doing underneath it all. And that, ladies and gentlemen, is the strange theory of light and matter. It's strange, but it's true. And it's how the world actually works. Thank you.